Good evening, everybody. Welcome to the next lecture. Today we'll be talking about EPT graphs, the edge intersection graphs of paths in a tree. Work that I've been involved with for the last 20 years or more. The story begins with a visit from a colleague of mine when I worked at Bell Labs. John Klintsewitz asked me, suppose you are routing telephone calls in a tree network where two calls interfere if they share an edge of the tree. How can you optimally schedule those calls? Well, here is a tree network, and here are two paths in the tree representing calls from one station to another. A call is a path between a node in this model, and a typical example might be of the intersection graph, where if two paths intersect, then they share an edge or a conflict in this graph. But intersection here will be taken a little bit differently from the intersection models that we've seen before. When we do that, a coloring for this graph will be a scheduling of those calls. So here we will make a distinction between two paths intersecting on a vertex or on an edge in that tree. And we will have two graph models, one being the vertex intersection graphs of paths in a tree, VPT, and the other being edge intersection graphs of paths in a tree, EPT. Each vertex in either graph corresponds to a path, and you have an edge in the VPT graph if the paths intersect on at least one vertex, and they conflict, or there's an edge in the EPT graph if they share one edge. Here in my example above, I have a tree with some paths, and you can see that in the VPT graph, there are more edges because some paths intersect on a vertex but not on a path. For example, you see that AD intersect, here they are, A is red and D is light blue. They intersect on this point, but only at a point. They don't share an edge. Therefore, in the EPG graph, they're not connected. Similarly, for DC, DC share a vertex, but not an edge. So the VPT graph will have the same vertices, more edges. Any edge in VPT would be an edge in EPT, but not vice versa. So to recap, if I have a situation like this where two paths share a vertex, then we say they vertex intersect, so they cause an edge in VPT. On the other hand, below, if they share an edge, then they intersect on an edge, and they create a conflict in the EPT. Okay. Now, we've studied about chordal graphs quite a bit in this course, and I just put their definition on the slide, although you know it very well. It's a graph that has no induced chordless cycles. And we saw the theorem that chordal graphs are exactly the vertex intersection graphs of subtrees of a tree. Now, a path is a certain kind of subtree. It's a very skinny one. Here's a representation of this chordal graph G on a tree. Okay, so because a chordal graph is intersection graph of paths of subtrees of a tree, certainly the vertex intersection graph of paths in a tree would be a chordal graph, but a special kind, a subclass of chordal graphs. And that's what's stated here. VPT, or path graphs, sometimes they are known as, are chordal, However, EPT graphs are not chordal, and they could have cycles of much larger size. Let's see how. Well, first observation is in an EPT representation, here I can get a cycle, let's say C6, in this fashion. You see that there's a star as my tree, and each path is a slice of this pi. I would call this the 6 pi. One goes in and out, two goes in and out, and they share an edge. Although they all intersect in that center point, it's not an edge intersection. So as you go around this representation, you get the graph C6. The interesting theorem is that if you have a EPT representation of a graph, then if it contains a chordless cycle, let's say Cm, then this representation must have a pi representing that cycle, meaning this is a unique representation for a chordless cycle. Now let's look at the question of restricting the degree of the host tree. If M is the maximum degree of the tree, then an EPT graph has no chordless M+1 cycle or larger. That follows immediately from that pi theorem, because if you have a maximum degree of M, that means slicing your pi, you can get M slices. But you can't get M+1 slices, and that's the only way to get a chordless cycle. So restricting the maximum degree of the tree restricts the number, the size, rather, of the chordless cycles. As a corollary, if you have an EPT representation on a degree 3 tree, then the graph is a chordal graph. Why? Because the smallest chordless cycle would be 3, and that is the definition of a chordal graph. So on degree 3 trees, we have this situation that then, and only then, is an EPT graph a chordal graph as well. Now you might ask, what kind of chordal graphs? Let's see. Okay. Let's look at the example of the complement of a 6 cycle. And we will see that this, as an example, requires degree 3 on my host tree. Why? Well, first of all, let's look at that outer cycle, A, B, C, D. By the pi theorem, it must be represented by a pi. A goes in and out, B goes in and out, C goes in and out, and D. Now let's try to fit in the other two vertices, x and y. Well, we can fit in x, because x has to be a neighbor of A and D. So x would be a path. It has to share with A and D. Here it is sharing on this upper. It also, and what does y have to do? It has to share with the existing vertices B and C, sharing this edge, and they have to share with each other. Well, if they're going to share with each other, they have to break out into a 5th branch. And that proves that I need degree 5 for my tree in order to represent this graph. So we know what cycles must look like. Let's look at cliques. There are 2 representations for cliques in the EPT graph. One is called a claw clique, and the other is called an edge clique. Here's an example of a claw clique. You have a tree that has a claw in it, 3 branches, and in the claw, all of the paths have to share 2 out of the 3. It has to come in and out, in and out, in and out. They always have some branch in the tree in common. Or they could be an edge clique where all of the paths share one single common edge. So here, again, I'm looking at K6. 6 paths all sharing this edge at the bottom gives me a clique, or 6 sharing two at a time edges in the claw. Here we have 6 and 1. Here we have 2 and 3. How about 2 and 5? Where do 2 and 5? Well, 5 is this blue, 2 is this red. They share on this branch. And the very nice characterization theorem for this is that if you have an EPT representation of the graph, if it contains a clique on M vertices, then that representation must contain either a claw or an edge. There are only 2 ways in order to get a clique. Well, that gives us some tools to use on how we might represent an EPT graph, looking at how to put down their claws, their cliques and claws or edges, how to put down their cycles as pies. And from that, we can get a number of different graphs that will not be in the class EPT. Now, I would like to state what I call the no-kissing lemma. If you have an EPT representation, P, on a tree, and U is any node of T, we may assume without lots of generality and without increasing the degree of the tree that all paths touching U continue through U. That is, no stopping, no kissing U. How would you do that? Well, suppose you have a representation like we have on the left, where you have some paths kissing, like E just touches C. Well, we can get rid of that kissing by shortening E, creating another vertex, shortening E. It didn't mess up any of its edge intersections, just a vertex intersection. And now, by doing this, on E and on A, I have this property that my paths never just touch each other. They are backed up so that they share edges. Well, we'll use that in the following theorem. If P is a degree 3 tree, binary trees, for example, binary trees like we use in searching are degree 3 trees, has 2 children and 1 parent. Then, by applying the no-kissing lemma to all of the nodes in a degree 3 tree, it would yield a VPT representation on this degree 3 tree. Why? Because I've eliminated any intersections that are just on a vertex. If you intersect on a whole edge. And I can do that on a degree 3 tree. So if I had an EPT representation, I can do this construction, pull back, and I get a VPT representation. That tells me that degree 3 EPT graphs are equivalent to degree 3 VPT graphs, which are also degree 3 EPT. They will be, therefore, chordal and EPT, right? They're degree 3 EPT, so they're degree 3 EPT. We've just shown that I can modify this representation to get a VPT representation. Now the next inclusion is clear. If it's degree 3 EPT, it's EPT. And if it's degree 3 VPT, it is chordal. You've seen that already. So now let's prove that this loop closes on itself. That is, that a graph that is both chordal and EPT will in fact be degree 3 EPT. Here's the proof. Take an EPT representation on a T, on T where the maximum degree is greater than 3. and let U be any node of the tree with this degree that's too big. Assume that the no-kissing lemma has been applied, and let U, capital U, denote all the paths passing through this vertex U. Let X be a simplicial vertex of the induced graph GU. Remember, my assumption are what? That the graph is chordal, that it's EPT, and I want to show that it's going to be degree 3 EPT. Oops. So I choose a simplicial vertex, which I can do since this is chordal. Let's look at it. All paths in U share an edge with PX, because this is a EPT representation. So here is X. Well, X is a path. Anything in its neighborhood has to share either one leg or the other leg. There are guys like the Y, guys like the Z. They are neighbors of X. But since it's simplicial, Z and Y also have to share an edge because they are supposed to be adjacent. So if Z is coming in from one direction, Y is coming in from the other direction, they're going to have to exit together. And since they're exiting, I can now take all of the neighbors of X, put them on one side, pull them across, create sort of a new dummy edge, like this. And now, what's Z doing? Z is coming in, it's going out. Y is coming in, going out. They share this bridge. All the paths sharing with X will share this bridge. And what did I do by this transformation? I've maintained the same graph, but I've reduced the degree of that vertex in the tree. Now, this is a vertex of degree 1 less than it was before, and I have another vertex whose degree is 3. So I repeat this over and over again until I've split all of the vertices in the tree that are higher than degree 3. That proves that I have a degree 3 representation. So to summarize, all of the 4 classes, chordal intersect EPT, degree 3 EPT, VPT intersect EPT, and degree 3 VPT are all the same. And this was the theorem that we proved in 1985 when I was visiting Clemson University. Well, actually, we proved it a little bit before that. By 1985 is when the paper got published. So you might ask, fine, what about degree 4? So let me tell you the result. 20 years later, we were able to prove another result, namely that the weakly chordal graphs intersected with the EPT graphs were precisely the degree 4 EPT graphs. And then the analogy between the yellow box on top and the boldened yellow box in the bottom is a very nice equivalence. So now I will go into that, something I didn't do on the first lecture. And now that you are familiar with some of these proof techniques, I'm going to walk it through this proof a little bit with you. Weakly chordal graphs are a class that are defined as having no chordless cycle Cm for m greater than or equal to 5, nor the complement of such a chordless cycle. We often call these holes and antiholes. And holes and antiholes of size 4 are allowed in weakly chordal, but 5 or larger are not. That's why they're called weakly chordal, because they're not they're not really chordal, they're just have this weaker condition. And there's a very nice theorem that characterizes weakly chordal graphs as those such that every induced subgraph of G is either a clique or has a two-pair. I'll tell you what a two-pair is. But again, this is a kind of weakening of the simplicial vertex theorem for chordal graphs. In chordal graphs, you always have a vertex that is simplicial. Here you're going to have a pair of vertices that have the following property. A two-pair is a pair of vertices such that every chordless path between them has length 2. So here is xy as a two-pair. On the right, xy is not a two-pair. Why? Because it has a path, a P4, longer than just two edges. So in the left, it is a two-pair. In the right, it is not a two-pair. If xy is a two-pair, notice that their common neighborhood is an xy minimal separator, just like we are familiar with from chordal graphs. Right? Their common neighbors certainly separate x and y, and you can't get rid of any, because if you forgot to put one of them in, you would still have the path. So the common neighborhood is an xy minimal separator. Here you see that it is, and here their common neighbors, of course, are not a separator. So let us look at this theorem for degree 4. If G has an EPT representation on a degree 4 tree, and that will happen if and only if it is a weakly chordal graph. Let's try to sketch the proof. In the first direction, let's assume that it's EPT and it has a representation on a degree 4 tree. By the pi theorem, G has no chordless cycle of length greater than or equal to 5. And that was our observation right at the beginning. If it has degree 5, if it has degree 4, it cannot have a 5 clique. And it cannot have a 5 cycle. Similarly, it can't have a 5 anticycle, because an anticycle is the same as a cycle on 5 vertices. If you just complement a C5, you'll get another C5. Okay, fine. So I have now shown that G has no C5 or C5 bar. What about bigger ones? Well, we already saw the example that C6 bar required degree 5. So it cannot be there. Moreover, by theorem in the Golombek-Jameson 85, it's very easy to see that an anticycle on M vertices for M greater than or equal to 7 is not an EPT graph. That proof has to do with the representations of cycles and cliques. And that shows that it's weakly chordal. Now look at the other direction. Suppose it is weakly chordal. Let P be an EPT representation on a tree with maximal degree D that is too big. We're going to do a kind of transformation, like we did in the previous theorem, to cut down the degree of a vertex U who's one of those bad nodes in the tree. It has degree D, which is too big. So we will transform our existing EPT representation into another one, P prime on T prime, with fewer vertices of degree D. And it'll be one of those stretching arguments like we saw before. The full proof follows by induction. If you can reduce one of them, then you can continue. So we assume the kissing lemma holds at U, and let capital U be the paths passing through vertex little u. Now the induced subgraph on those vertices U is weakly chordal, because being weakly chordal is a hereditary property. If a whole graph is, then an induced subgraph is. And so there are going to be two cases. Either this induced graph is a clique, or it has a two-pair. First case is that it is a clique. If this clique that we have were to be a claw clique, then U would have degree 3, and we would be done. Because we're looking at all the paths that go into U and out of U. So if this was a claw clique, then U would have degree 3. All the other edges would be irrelevant. You could erase them. So we would be done. So we have to look at the case where this is an edge clique. That is, all the paths in U share one single edge, at least. Call it V1, U. And we will perform a transformation. So here, this edge that's colored red is shared by all the paths that are neighbors of U. Okay. So we take this edge, put a dummy vertex, W, on it, and any edge, like this turquoise one, gets moved over to go from itself to the dummy and then on to U. And paths that somehow just come in and don't use this, they all come in and use this. So the ones that well, let's look at it more clearly in the text. If if GU has a two-pair XY, right. So this is what it looks like for this vertex that we're trying to reduce its degree, and this transformation will reduce the degree. Now we have to see how we extend our paths. If it has a, well, it does have a two-pair. The common neighborhood S of that two-pair is a minimal separator. And it splits GU into at least two connected components, GX containing X and GY containing Y. And the star edges centered at U are now painted. The two edges that the two that are contained in PX are red, and those in PY are blue. And we propagate this coloring to other star edges via natural kind of propagation, where if PZ has one red edge, then paint all its other star edges red. And PZ has one blue edge, then paint its other star edges blue. And no star edge will get two colors. Okay. Here, let's illustrate. If the vertices that are induced by the separator are a clique, then you see that it's separating X and Y. We perform this transformation. Here we have X, Here we have y. Remember, they are not adjacent, therefore they only touch u. V, let's say, is a neighbor of x. So v is sharing with x. It is not sharing with y because it's separated by the separator. So when it comes into u, it goes out some other branch. It does not share an edge with y. There are other edges like this that share something with x and something with y. They are the common neighbors in the separator. So here's what we shall do. We shall split u into two nodes, u prime and u double prime. Y goes along with u double prime. X goes along with u prime. Anything like v that comes into u and goes out and doesn't share with y just comes into u prime and goes out its way. And those common neighbors from the separator share the new edge just like this. So you can see that this transformation clearly leaves the graph unchanged and reduces the degree of u. That would be in the case that GS is a clique. If GS is not a clique, remember this is not a chordal graph, so separators are not necessarily cliques. If it's not a clique, like we have here, then there exists a path from, say, this vertex V that is in the x side that contains only one of the edges, V1u, V2u, V3u, V4u. Let's say V1u. So looking at this picture here, where is my vertex, my V? It's here. It's sharing something with x, and it's going out its own way. Look at those vertices 1, 2, 3, 4. Those are the first vertices on the path going from u to v in this, into u in y in this direction, y in this direction, x in this direction, x in this direction. So this v shares only one of these four edges of this four-claw. So let's just assume, as in the diagram, it's sharing this edge. Now we color the edges as follows. V1u is not colored. VIU for I greater than 5 is colored pink if it is contained in some path in R. And it is colored if it's contained in a path that already has some pink edges. So pink is sort of propagating this, all the edges that touch this whole configuration. And this is supposed to convince you that all of these edges will go off into different directions, and that this sort of propagation allowed the transformation that you now see on the right. We take U, we split this edge with a dummy W. All these sort of pink edges, they're sort of red in this, these pink edges get moved off to the dummy. All the other edges stay where they were. I've lowered the degree of U, and I've maintained the same graph without having added new edges in the EPT graph or deleted any. Well, that's the outline of the proof. I don't expect that you followed every detail. To see the details, you would need to go back to the paper to read it more carefully. But this is basically the idea, that we're using the fact that we have the two pair, that we are able to go through these cases in order to do transformations that lower the degree of one of the high degree vertices. And then we continue by induction. Okay, so now the story continues. We investigated some of the algorithmic properties of EPT graphs. The recognition and the coloring problems for EPT graphs are NP-complete. Tarjan found a 3-halves approximation algorithm for coloring them. On degree 3 hosts, well, and also on degree 4, we know that coloring would be polynomial. And the reason is we already have in our pockets coloring algorithms for chordal graphs and for weakly chordal graphs. And so those cases can be colored optimally. Moreover, the max clique and max stable set are also polynomial for EPT graphs, no matter what the degree is. Okay, so Jameson didn't leave it there. He decided to go a little bit further and say, investigate a more general question, something that we will call HST graphs and their representations. Now we're going to move from just paths on a tree to subtrees on a tree, but subtrees with the edge intersection model in mind. So we'll say that a collection of subtrees T will satisfy H being the maximum degree of its host. S is the maximum degree of a subtree. And T will give you an edge in your intersection graph if the subtree X and Y share at least T vertices. So if T was equal to 1, they only have to share one vertex. Then we would have subtrees of a tree, and we would have chordal graphs. If T is equal to 2, then we're getting to edge intersection. Sorry, T equals 3. Yeah, if they share 1, they intersect on a point. If they share 2, then they would be edge intersection. And they even allow T to be greater than that. So in this nomenclature, it's very easy to see that interval graphs are the family 2, 2, 1. Why? Because your host is a line, so the host is one string with degree 2. Your intervals, therefore, have degree 2. And intersection is on a vertex. So interval graphs is 2, 2, 2. In fact, interval graphs could also be 2, 2, 2, 2, 2 or 2, 2, 1, because in interval graphs it really wouldn't matter. Why? Because they are degree less than 3. EPT graphs that we just studied would have edge intersections, so conflict means 2 vertices. The objects are paths, so they have degree 2. And the tree itself has no constraint on its degree. It could be infinity. So EPT in this nomenclature is infinity, infinity 2. Chordal graphs are infinity, infinity 1. No constraint on the degree of the tree, no constraint on the degrees of the subtrees, and vertex intersection. And one can show, there are 2 references that show this, that they are actually equivalent to 3, 3, 1 and 3, 3, 2. That is, degree 3 host, degree 3 objects, edge intersection, or vertex intersection. So this was shown not in a trivial manner. Here are some more. Any graph, turns out, is infinity, infinity 2. You can just take a star and as your host, and you can let your subtrees be whatever they want, and you can realize any graph. And we just saw two results in our lecture so far, that EPT intersected with chordal is equal to 322, 321. And we saw that EPT intersected with weakly chordal is 322. So there are now two directions you could generalize EPT graphs. One would be to keep T as edge intersection constant and increase your S, see what happens, but try to keep a bound on H. Or you could increase the parameter T as a constant tolerance, keep S as 2 paths, and see what you get. So we're finding new classes of graphs depending on how you mess around with your parameters. So here is a theorem where we characterized the 442 graphs in terms of forbidden subgraphs. So the characterization is that 442, so your host is degree 4, your subtrees are any kind of subtree in a degree 4 tree, and you require edge intersection. That's equal to the weakly chordal graphs that are free of K23, P6 complement, 4P2 complement, etc., etc., and these also three graphs. Well, that is a nice but maybe a little bit cumbersome way to check, but it is a nice characterization for the class 442. In fact, these are not just graphs as they appear. Each one of these K1, K2 could be either a single point or an edge. The point is we have a forbidden subgraph characterization. And these are those forbidden graphs. Another direction is to increase the tolerance and keep paths. For this, we looked at what we would call KEPT graphs, and this is simply the following. Your objects are paths on a tree, but now, in order for two paths to conflict or give you an edge in your conflict graph, your intersection graph, they have to share at least K edges. So in this representation, we have this pink-colored intersecting the blue with only K-1 edges. So in my conflict graph, C and B are probably not connected. And sure enough, when I look over here, they were not connected. So formally, XY is an edge in the KEPT graph if their paths, PX and PY, intersect on at least K edges in the tree representation. And it's a KEPT graph if G has a K representation. So we have our our sort of hierarchy where here we had paths sharing a single vertex. We got VPT, a single edge. We got one EPT, or what we called EPT, or K edges, KEPT. What are some of the properties? Well, first of all, one EPT, of course, is contained in KEPT, but it's properly contained for any fixed K. And we can divide any edge into K edges by adding dummies. When restricting to 3-degree trees, this containment is also strict. One EPT is not equal to KEPT. And here is an example. Here we have a representation of this graph but you have a theorem that would tell you that this graph is not one EPT. Can you tell me why this is not EPT? What does it have going around? It has a chordless cycle. The only representation in one EPT, an EPT, is a pie. So I bring you a pizza, and it's sliced into 6 pieces. And now that's fine for the outer. Now I want to insert G that is going to hit only an edge with A and D. Well, you couldn't do that with that pizza. Why? Because A is a slice. One piece of that slice shares with B, and one shares with F. So there's no way G could hit only A and not hit its neighbors, and D and not hit its neighbors. But this tree, notice, also is degree 3. So this has a degree 3 KEPT graph representation. Some other properties, VPT are incomparable with KEPT. There are graphs that go on both sides. When restricted to degree 3, we know that VPT is equal to KEPT for any fixed K. And chordless cycles are degree 3 KEPT for any K. Maximal cliques, well, they have a similar characterization as they did in EPT. Either they have to share a string of K edges, or they have to share branches of this sort of K claw. One of these KEPT has at most vertices cubed maximal cliques, telling you that you can do the clique problem in polynomial time. Of course, it's NP complete to do coloring. And then there's a recognition algorithm, which we will not go into. Right. As I said, coloring will be NP complete. And the following graph is not a KEPT graph, just so that you know that there are some examples that are not. And some open questions is actually whether this hierarchy going from KEPT to K plus 1 EPT is strict all the way up. I would conjecture that it is. Now, Jameson and his partner on these HST representations introduced an idea of a property called orthodox representations. For every path, its endpoints are leaves, and 2 paths share a leaf if and only if vertices I and J are adjacent in the graph. I'll just tell you the result that we have. And that is, the following statements are equivalent. G is chordal if and only if G has a 3-3-1 representation, if and only if it has an orthodox 3-3-1 representation, if it has a 3-3-2 representation, and an orthodox 3-3-2 representation. These are from McMorris-Scheinemann and Jameson-Mulder. And they showed some other theorems, like it has an orthodox VPT if and only if it has orthodox VPT restricted to degree 3, and it has an orthodox 1 EPT representation restricted to 3 trees. Okay, this is kind of a summary of too much details, but know that there is a hierarchy of all of these different classes that one can write. Here on the right, we see some familiar things like EPT degree 3 being equivalent to VPT. This is one theorem we saw. Here it's the same thing in its HST notation. We see weakly chordal up here, and we see different kinds of EPT and orthodox guys. This is a complete hierarchy, meaning anything that looks like it's not above another is really not. Just proving that this is a complete hierarchy takes a bit of work, because for every pair that's incomparable, you have to find somebody above and below, and on the other way, above and below. Okay, here's another picture of it. And some further research, people might want to characterize other families of HST graphs for various other HSTs. And in the most recent paper by Michal, Marina, Elad Cohen, and myself, we sort of finished off all of the HSTs for H4 and the other parameters being 1, 2, 3, or 4. So now all of those are characterized. And I doubt that anybody really wants to try to go and do H5 and try to study those, but you never know. One question might be whether weakly chordal fits into this category. Is there some filling in of these question marks to give you weakly chordal? The answer to that is no. We found that that's not true. And so I thank you very much. And then I would like to close this lecture with a few words to you students and to you out in Cyberland. So I retired this year from administration and teaching regular classes at the university on my birthday. And this has been a great opportunity to allow me to travel and to give lectures and short courses like I'm giving here at IIT Kharagpur and elsewhere around the globe. It's jolly good fun. And it's also given me time to be able to sing as a poor player upon the stage. So thank you for attending and listening to the lecture. I'll see you tomorrow, and tomorrow, and tomorrow. So now go off and finish off that quotation. Thank you.